So this is the third in a little sequence of revision of AS Further Maths matrices work or ideas in preparation for looking at further work on matrices in the A2 content. We've had a look so far at how to multiply two matrices together and how to find the determinant of a 2x2 matrix. So in this one, I want to have a look at the inverse of a 2x2 matrix, and a word just at the beginning of why we need to do this, or what the purpose of an inverse matrix is. So having defined and shown you how to multiply two matrices together, the perhaps natural follow-on question or thought from that is, well, what if I want to divide one matrix by another one, or how do I undo a multiplication of two matrices, or that kind of thing? And this is where the inverse matrix comes in. There is no definition, there is no procedure for dividing by a matrix. And so we think about multiplying by an inverse matrix. So very much like, if you take a number, 8, for example, rather than dividing by 8, we can think about multiplying by its reciprocal, 1 over 8. And this is the same kind of thing going on here. I know that it's 1 over 8 that I need to multiply because 8 times 1 over 8 gives me 1. And the point of the inverse of a 2x2 matrix is that it is the matrix that I would need to multiply the original matrix by in order to get the equivalent of 1 from in a matrix situation. So it's worth saying at this point that we talk about the identity matrix, or, well, specifically for the purposes of what we're thinking about here, a 2x2 identity matrix. Which I might call I, or possibly I with a little 2 suffix in the situations where I might be thinking about other square matrices. We're only going to be doing this with square matrices. It doesn't make sense to talk about them if they're not square. So I might use the suffix on the I there to talk about the dimensions of it. And the identity matrix is the square matrix that has ones in what is known as the leading diagonal. That's top left to bottom right. So it has ones there and zeros everywhere else. So that's a 2x2 identity matrix. Similarly, I can get 3x3 or whatever else it might be, m by m identity matrices, and they would just have ones down that left to right, top left, bottom right diagonal, and zeros everywhere else. That's an identity matrix, and it's equivalent to a 1 because if I take any 2x2 matrix and I multiply it by this 2x2 identity matrix, the result is unchanging. It doesn't change the matrix. So like multiplying by 1, essentially, when we're talking about numbers. And that's why it's a significant thing. So the point of an inverse matrix is to find, if I start with some matrix and I want to know what would I need to multiply it by in order to achieve the identity as the outcome, then the thing that I need to multiply it by is the inverse of the original matrix. Notation-wise, an inverse because I'm only thinking about 2x2 matrices. Supposing I've got a matrix A, 2x2 matrix A, then its inverse we denote by, very common with in common with lots of other use of kind of inverse type things, like inverse trig functions and that sort of thing. We use it looks like a power of -1. Again, this is important, like we did with some of the trig things. Important not to confuse reciprocal and inverse. In the case of scalar numbers, the two things are the same as each other, but that's only in the case of scalar numbers, or generally only in the case of scalar numbers. If I use a power of -1 like that on a matrix in my notation, then I don't mean it to be 1 divided by my matrix A, because I don't know how to divide by a matrix anyway. But what I do mean is the inverse of the matrix, very much like the trig thing. So when we talk about cos to the -1 of something, I don't mean 1 over cos of the thing. I mean the inverse cos, inverting the cosine function. And in this case, what I'm doing is I'm inverting a matrix. So very straightforward thing to do for a 2x2 matrix. So if I have a matrix M, like we did when we were finding the determinant, let's go for A, B, C, D. Don't forget that we can calculate the determinant, det M, by doing AD minus BC. And I can find the inverse matrix, M minus 1. What I have to do is I have to have a scalar multiple, which is 1 over det M. And then I need to have a 2x2 matrix alongside it here. And to work out what entries go in this 2x2 matrix here, what I do is I take the leading diagonal from the original matrix M. So that's the A and D there, and I swap them around. So that becomes D and A there. And then I look at the other diagonal where the B's and C's are. I don't swap those around, but what I do is I change the signs of both of them. Minus B and minus C like that. And that produces my inverse matrix. Don't forget, of course, that if either B or C are negative, then changing the sign of them, saying minus B and minus C, is just going to make them positive instead. Notice as well about this bit here. Quite a common error is to get so sort of familiar, become so routine, so mechanical about the process of finding an inverse matrix. Quite a common error is that people forget that this fraction, generally speaking, a fraction outside the rearranged matrix, the fraction as a whole is not the determinant. It's the bottom of the fraction there that's the determinant, or at least the 1 over the whatever the number on the bottom of 1 over something is, that's the determinant of this matrix, not the entire fraction, just the bit under the 1. So that's how we go about finding an inverse matrix. Let's just do a quick example. So, for example, well, let's take that one that we did multiplying there, 6, 5, 1, 2. And find its inverse, a to the minus 1. So the first thing I would do would be to calculate the determinant, which we did before, but let's just remind ourselves. 6 times 2, take away 5 times 1. 12 take away 5 gives me 7. And then once I've done that, it's very straightforward just to get the inverse. I can just write that down now. A to the minus 1 must be 1/7. And then swap around the 6 and the 2. So we've got a 2 and a 6 in that leading diagonal. Change the sign of the other two entries, -5 and -1, like that. And if necessary, if you want to, it's not always most appropriate, but if you want to, you can put the fraction inside the matrix by multiplying each element inside the matrix by the fraction or by whatever you've got outside it, whatever the scalar value you've got outside it, whatever 1 over determinant there. So we could have this as 2/7 -5/7 -1/7 and 6/7. Not always necessary to do that, and very often more confusing when you do that, because you end up, depending on what you have to do with it afterwards, you might well have to be multiplying this by something else, by another matrix or something, and then we're having to manipulate all sorts of fractions. So think about what you're going to do with it, whether you want to have that 1 over the determinant scalar inside or out, left inside or outside the resulting inverse. So there we are. That's how we go about finding the inverse of a 2 by 2 matrix.